Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the depths of theoretical physics, few concepts challenge our understanding of reality as profoundly as the multiverse theory. This isn't science fiction. It's a serious scientific hypothesis that suggests our universe, with its 100 billion galaxies and countless stars, might be just one of infinitely many universes existing in a vast cosmic ensemble. The multiverse concept emerged from some of the most successful theories in modern physics. When physicists in the early 21st century began connecting quantum mechanics with cosmology, they discovered that several independent lines of research were pointing toward the same startling conclusion. Our universe might not be unique. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. To understand the multiverse, we must first grasp what makes it scientifically credible. Unlike purely speculative ideas, multiverse theories arise naturally from established physics. They're not invented to solve philosophical problems. They emerge as inevitable consequences of our best theories about quantum mechanics, cosmic inflation, and string theory. The term multiverse itself encompasses several distinct concepts. Some versions suggest parallel universes, where every quantum event creates branching realities. Others propose bubble universes forming during cosmic inflation, each with potentially different physical laws. Still others emerge from string theory's vast landscape of possible configurations. What unites these theories is their foundation in rigorous mathematics and their connection to observable phenomena. The cosmic microwave background radiation, detected by satellites like the Wilkinson Microwave Anisotropy Probe and Planck, provides clues about the early universe that support inflationary cosmology, the same theory that naturally leads to eternal inflation and bubble universes. Quantum mechanics, tested to extraordinary precision in laboratories worldwide, suggests that reality operates fundamentally differently than our everyday experience suggests. At quantum scales, particles exist in superposition states, occupying multiple possibilities simultaneously until measured. This quantum behavior, scaled up through various theoretical frameworks, leads to multiverse scenarios. The scientific method requires that theories make testable predictions. While we cannot directly observe other universes, multiverse theories make predictions about phenomena we can observe. These include patterns in the cosmic microwave background, the distribution of matter in our universe, and the values of fundamental constants. Consider the fine-tuning problem. Many physical constants appear precisely calibrated for life. The strength of gravity, the mass of electrons, and the rate of cosmic expansion all fall within narrow ranges that allow stars, planets, and complex chemistry to exist. In a single universe, this might require explanation. In a multiverse with varying physical laws, our universe's life-friendly properties become a selection effect. We observe them because we exist to do so. The implications extend beyond physics into philosophy and our understanding of human significance. If infinite universes exist, containing every possible variation of events and outcomes, what does this mean for free will, identity, and the nature of existence itself? Modern cosmology has already expanded our cosmic perspective dramatically. We've learned that Earth orbits an ordinary star in a typical galaxy, among billions of others. The multiverse theory suggests this pattern of cosmic humility continues. Our entire observable universe might be an infinitesimal part of a much grander structure. This scientific journey requires careful distinction between evidence-based theorizing and speculation. The multiverse theories we'll explore emerge from established physics, not wishful thinking. They represent humanity's attempt to understand the deepest questions about reality using our most powerful mathematical and experimental tools. As we embark on this exploration, we'll examine how quantum mechanics, cosmology, and string theory independently point toward multiverse scenarios, what evidence supports these ideas, and what they might mean for our understanding of existence itself. The quantum multiverse begins with one of physics' most profound mysteries, the measurement problem. When quantum particles exist in superposition, occupying multiple states simultaneously, what happens when we observe them? This question led physicist Hugh Everett III to propose one of the most radical ideas in science, the many worlds interpretation. In 1957, Everett suggested that quantum measurements don't collapse superposition states into single outcomes. Instead, reality branches into parallel universes, each containing one possible measurement result. Every quantum event creates new universes, spawning an ever-expanding tree of parallel realities. Consider the famous thought experiment of Schrödinger's cat. In the traditional interpretation, the cat exists in superposition, simultaneously, alive and dead, until observed. Everett's interpretation suggests something far more extraordinary. The universe splits into two branches. In one branch, the cat lives. In another, it dies. Both outcomes are equally real, existing in parallel universes. This isn't mere philosophical speculation. The many worlds interpretation emerges naturally from the mathematics of quantum mechanics. The Schrödinger equation, which governs quantum systems, is completely deterministic and never mentions wave function collapse. It describes reality as a constantly branching wave function where all possibilities coexist. Laboratory experiments consistently demonstrate quantum superposition and entanglement, phenomena that seem to require the existence of multiple simultaneous realities. The double-slit experiment shows single photons interfering with themselves, suggesting they travel through multiple paths simultaneously. Quantum computers exploit superposition to perform calculations impossible for classical computers, processing multiple solutions in parallel. The scale of this branching defies imagination. Every quantum interaction in every atom throughout the universe potentially creates new branches. With approximately 10 to the power of 80 atoms in the observable universe, each containing countless quantum interactions every second, the branching rate is astronomical. Within fractions of a second, the number of parallel universes could exceed 10 to the power of 10 to the power of 50. These parallel universes remain causally disconnected. We cannot communicate with or travel between them. The branches that split from quantum measurements never reunite. This isolation explains why we experience a single, consistent reality, despite the constant branching occurring around us. The many worlds. Interpretation solves several quantum puzzles without requiring mysterious wave function collapse. It explains the apparent randomness of quantum measurements. Outcomes aren't truly random. They're determined by which branch of reality we happen to inhabit. The probabilistic nature of quantum mechanics reflects our ignorance about which branch we're in, not fundamental randomness in nature. Experimental evidence supporting many worlds comes from quantum decoherence research. When quantum systems interact with their environment, they rapidly lose coherence and appear to collapse into classical states. However, the full quantum wave function continues evolving according to Schrödinger's equation, with different outcomes existing in separate branches. Recent advances in quantum error correction and quantum computing provide new tests of many worlds predictions. These technologies rely on maintaining quantum superposition in large-scale systems, effectively accessing computational resources from parallel universes. IBM's quantum computers and Google's quantum supremacy experiments demonstrate quantum effects at unprecedented scales. The implications are staggering. In some branch of the quantum multiverse, every possible version of history has played out. There are branches where dinosaurs never went extinct, where you made different life choices, where historical events unfolded differently. Every possible arrangement of matter and energy that doesn't violate physical laws exists somewhere in the quantum multiverse. Critics argue that many worlds is unscientific because parallel universes cannot be directly observed. However, the theory makes testable predictions about quantum interference patterns, decoherence rates, and the behavior of quantum computers. These predictions have been consistently confirmed by experiments. The quantum multiverse also connects to other multiverse theories through quantum cosmology. If the universe itself is a quantum system, then cosmic events like inflation might create quantum superpositions of entire universes. This bridges the gap between quantum mechanics and cosmological multiverse theories. Modern quantum field theory suggests that even empty space contains quantum fluctuations, virtual particles popping in and out of existence. In the many worlds framework, these fluctuations represent branches where particles exist in some universes, but not others. The quantum vacuum becomes a dynamic multiverse of possibilities. As we delve deeper into multiverse theories, we'll see how quantum mechanics connects with cosmic inflation to suggest even grander scenarios. Not just parallel versions of our universe, but entirely different universes with different physical laws and properties. The cosmic multiverse emerges from one of cosmology's greatest triumphs, inflation theory. In 1980, physicist Alan Guth proposed that the early universe underwent a period of exponential expansion, solving several cosmological puzzles. This inflationary epoch, lasting less than a second, stretched tiny quantum fluctuations into the large-scale structure we observe today. Inflation explains why the universe appears so uniform in temperature and density across vast distances. Without inflation, regions of space we observe today would never have been in causal contact, making their similar properties mysterious. Inflation also explains why space appears geometrically flat and why we don't observe exotic relics, like magnetic monopoles predicted by grand unified theories. The evidence for inflation comes from precise measurements of the cosmic microwave. Background radiation. The Planck satellite and other experiments have mapped temperature fluctuations that match inflation's predictions with extraordinary accuracy. These fluctuations, originating from quantum noise during inflation, became the seeds for galaxies and larger structures. However, inflation theory leads to an unexpected consequence: eternal inflation. The same quantum fluctuations that create density variations also affect the inflation field itself. In some regions, quantum fluctuations cause inflation to end, forming universes like ours. In other regions, inflation continues exponentially, creating more space that can undergo further inflation. André Linde developed the theory of chaotic inflation in the early 1980s, showing that inflation naturally becomes eternal. Once inflation begins anywhere in space, it produces exponentially expanding regions where inflation continues forever. These regions spawn bubble universes, distinct cosmic domains where inflation has ended and normal physics applies. The mathematics of eternal inflation are compelling. The rate of space creation through continued inflation vastly exceeds the rate at which bubble universes form. This means inflation never truly ends globally, even though it ends locally within individual bubbles like our universe. The process continues infinitely, generating an endless succession of bubble universes. Each bubble universe could have different physical properties. The fundamental constants, particle masses, and even the number of spatial dimensions might vary between bubbles. This variation arises from the different ways that quantum fields can settle into their ground states as inflation ends in each bubble. Our observable universe, extending roughly 46 billion light-years in all directions, represents only a tiny fraction of our bubble universe. The entire bubble could be vastly larger, possibly infinite in extent. Beyond our bubble's boundaries lie other bubbles, each containing their own space-time domains, with potentially different physics. The scale of the eternal inflation multiverse defies comprehension. If our bubble universe is already unimaginably large, the multiverse containing all bubbles is infinitely larger. The volume of space undergoing inflation doubles every tiny fraction of a second, creating exponentially more room for new bubbles to form. These bubble universes remain causally disconnected. Light from other bubbles cannot reach us, because the space between bubbles continues expanding faster than light can travel. We cannot observe other universes directly, but eternal inflation makes testable predictions about our own universe's properties. One prediction involves the distribution of density fluctuations in the cosmic microwave background. Eternal inflation suggests these fluctuations should follow specific statistical patterns, which observations have confirmed. The theory also predicts that space should be very close to geometrically flat, matching precise measurements. Recent Researchers explored whether bubble collisions might leave observable signatures. If our bubble universe collided with another during its early expansion, this event might create distinctive patterns in the cosmic microwave background. Several research groups have searched for such signatures, with mixed results requiring further investigation. The anthropic principle becomes relevant in the eternal inflation multiverse. If bubbles have random physical properties, most would be unsuitable for life. We necessarily observe a bubble with life-friendly physics because we exist to observe it. This explains apparent fine-tuning without requiring special creation or design. String theory provides additional support for eternal inflation. The string landscape, the vast number of possible vacuum states in string theory, suggests that different bubble universes could explore different regions of this landscape. Each bubble would have distinct particle physics and forces. Eternal inflation also connects to quantum mechanics through quantum cosmology. The entire inflationary process involves quantum fields, and the bubble formation process might create quantum superpositions of different universes, bridging eternal inflation with many worlds scenarios. The implications challenge our cosmic perspective once again. If eternal inflation is correct, our universe is just one bubble in an infinite sea of bubbles, each potentially containing billions of galaxies and countless worlds. This cosmic democracy suggests that every possible arrangement of matter and energy that can exist does exist somewhere in the multiverse. As we continue exploring multiverse theories, we'll examine how string theory provides yet another pathway to infinite universes through its landscape of possible physical laws and dimensions. String theory, humanity's most ambitious attempt to unify all fundamental forces, has led to perhaps the most exotic version of the multiverse. This theory suggests that the basic building blocks of reality aren't point particles, but tiny vibrating strings existing in multiple dimensions beyond our familiar three-dimensional space. The mathematical consistency of string theory requires extra spatial dimensions, 6 or 7 beyond the 3 we experience. These additional dimensions are compactified, curled up so small that we cannot detect them directly. The way these dimensions fold and connect determines the physics we observe, including particle masses, force strengths, and the fundamental constants of nature. Leonard Susskind and other theorists discovered that string theory allows an enormous number of ways to compactify the extra dimensions. Each different configuration creates a distinct vacuum state with its own physics. The collection of all possible vacuum states forms what physicists call the string landscape, a vast space of possible universes. Early estimates suggested the string landscape might contain 10 to the power of 500 different vacuum states. Each state represents a potential universe with its own particle physics, forces, and physical laws. This number dwarfs the estimated 10 to the power of 80 atoms in our observable universe, creating an almost incomprehensibly large space of possibilities. The mathematical structures describing compactified dimensions are called Calabi-Yau, manifolds named after mathematicians Eugenio Calabi and Xing-Tung Yau. These complex geometric shapes determine how the extra dimensions fold back on themselves. Different Calabi-Yau manifolds produce different physics in the resulting four-dimensional spacetime. Even small changes in the shape or topology of these manifolds can dramatically alter the resulting physics. The number of particle types, their masses, the strength of forces like electromagnetism and gravity, and even the cosmological constant can all vary across the landscape. Most configurations would create universes utterly unlike our own. The string theory multiverse connects naturally to eternal inflation. During inflation, different regions of space might settle into different string vacuum states as they expand and cool. This creates a patchwork multiverse where different regions have different fundamental physics, determined by which valley of the string landscape they occupy. This resolves the landscape problem, the question of why our universe has its particular physical laws. Instead of requiring a unique theoretical explanation for our specific physics, the landscape suggests that all possible physics exist somewhere. We observe our particular set of laws because they allow observers like us to exist. The anthropic principle becomes crucial in the string landscape. Most vacuum states would create universes hostile to life. Stars might not form, atoms might be unstable, or the forces might be too strong or weak for complex chemistry. The vast majority of the landscape remains uninhabitable, but the sheer number of possibilities ensures that some regions support life. Our universe appears to occupy a rare, life-friendly region of the landscape. The cosmological constant, the energy density of empty space, has a value that allows galaxies to form without preventing structure formation. In most string vacua, this constant would be enormously larger, creating universes that expand too rapidly for matter to clump together. Recent research in string theory has explored whether transitions between different vacuum states might be possible. Quantum tunneling could potentially allow universes to jump from one region of the landscape to another, changing their fundamental physics. These transitions might create expanding bubbles of new physics within existing universes. The mathematical complexity of string theory presents both opportunities and challenges. While the theory provides a unified framework for all fundamental forces, including gravity, the calculations required to extract specific predictions remain extraordinarily difficult. Most of the string landscape remains unexplored mathematically. Experimental. Tests of string theory face significant challenges. The energy scales where string effects become important are far beyond current particle accelerators. However, string theory makes predictions about cosmology, black holes, and quantum gravity that might be testable through astronomical observations and precision experiments. Some string theorists have proposed that the landscape might be finite rather than infinite. If string theory has additional constraints that haven't yet been discovered, the number of possible vacuum states might be much smaller than current estimates suggest. This would make the anthropic explanation for our universe's properties less compelling. The holographic principle emerging from string theory research suggests that information in any volume of space can be encoded on its boundary surface. This principle implies that our three-dimensional reality might be a projection from information stored on a two-dimensional surface, adding another layer to our understanding of reality's structure. Advanced theoretical work explores whether different regions of the string landscape might be connected through higher dimensional spaces or wormholes. If such connections exist, information or even matter might potentially travel between universes with different physics, though such travel would likely be highly constrained. The string theory multiverse represents the ultimate expression of cosmic democracy. If correct, it suggests that every mathematically consistent set of physical laws exists somewhere in the multiverse. Our universe, with its specific particles and forces, represents just one possibility among an almost infinite number of alternatives. As we approach the final part of our exploration, we'll examine what evidence might support these multiverse theories and what their implications might be for humanity's place in the cosmic order. The search for multiverse evidence requires extraordinary creativity because we cannot directly observe other universes. However, each multiverse theory makes predictions about phenomena we can observe, providing indirect ways to test these radical ideas about reality's structure. The cosmic microwave background radiation provides our best window into the early universe and potential multiverse signatures. The Planck satellite has mapped temperature fluctuations with unprecedented precision, revealing patterns that support inflation theory. Some researchers have searched for circular patterns that might indicate bubble universe collisions, though results remain inconclusive. Variations in fundamental constants across space could signal different regions of the string landscape. The fine structure constant, which determines the strength of electromagnetic interactions, has been measured in distant galaxies using telescopes like the Very Large Telescope. Some studies suggest slight variations, though these results are controversial and require confirmation. Dark energy observations provide another potential multiverse test. The cosmological constant's value appears finely tuned for structure formation. If it were much larger, galaxies couldn't form. In a multiverse with varying physical laws, this apparent fine-tuning becomes a selection effect rather than a cosmic coincidence. Quantum experiments continue probing the foundations of reality. The largest quantum computers now maintain superposition, states involving hundreds of quantum bits, effectively accessing computational resources from parallel universes according to many worlds theory. Future quantum computers might test multiverse predictions more directly. Gravitational wave detectors like LIGO and Virgo have opened new observational windows. These instruments might eventually detect exotic signatures from cosmic strings, phase transitions, or other phenomena connected to multiverse physics. The planned space-based LISA detector will explore even more sensitive gravitational wave signatures. The implications of multiverse theories extend far beyond physics into philosophy, ethics, and human meaning. If infinite universes exist containing every possible outcome, what does this mean for moral responsibility and the significance of our choices? These questions challenge traditional notions of uniqueness and purpose. Some philosophers argue that the multiverse actually increases the importance of ethical behavior. If our actions are repeated infinite times across different universes, the total moral weight of our choices becomes enormous rather than diminished. Every kind act creates infinite kindness. Every harmful act creates infinite harm. The anthropic principle, central to many multiverse theories, remains controversial. Critics argue that it's unscientific because it cannot make falsifiable predictions. Supporters counter that it provides the only plausible explanation for apparent fine-tuning in physical constants without invoking supernatural intervention. Religious and spiritual perspectives on the multiverse vary widely. Some see infinite universes as compatible with divine creation, suggesting that God's creativity extends beyond a single universe. Others view multiverse theories as eliminating the need for divine fine-tuning. Most religious traditions are still grappling with these cosmological developments. Future experiments and observations will continue testing multiverse predictions. The James Webb Space Telescope is already revealing the early universe's structure, potentially constraining inflation models. Next-generation cosmic microwave background experiments will search for more subtle signatures of bubble collisions or cosmic strings. Particle physics experiments at the Large Hadron Collider and future accelerators might discover extra dimensions or other phenomena predicted by string theory. The discovery of supersymmetric particles would strongly support string theory and its multiverse implications. Advances in quantum computing and quantum error correction will provide new tests of many worlds' predictions. If quantum computers can consistently access exponentially large computational spaces, this would support the existence of parallel universes where different calculations occur simultaneously. Theoretical developments continue refining multiverse models. New mathematical techniques are exploring the string landscape structure, potentially reducing the number of possible vacuum states. Research into quantum gravity might reveal whether different types of multiverse theories can be unified into a single framework. The search for extraterrestrial life adds another dimension to multiverse considerations. If life is common throughout our universe, this might support theories suggesting that life-friendly physics is more probable than previously thought. Conversely, if life is extremely rare, this might strengthen anthropic arguments for multiverse theories. As humanity's cosmic perspective continues expanding, we must grapple with the possibility that our universe, already almost unimaginably vast, might be infinitesimal compared to the full scope of reality. This cosmic humility echoes previous revolutions that displaced Earth from the center of the solar system from the center of the galaxy, and our galaxy from the center of the universe. The multiverse theories we've explored represent humanity's latest attempt to understand reality's deepest structure. Whether they prove correct or not, they demonstrate the power of human creativity and mathematical reasoning to explore concepts that challenge our most basic assumptions about existence. These ideas remind us that science is fundamentally about asking profound questions and following evidence wherever it leads, even when the answers challenge our intuitions about reality. The multiverse may be the ultimate expression of nature's creativity, infinite universes exploring every possibility allowed by the laws of physics. As we continue pushing the boundaries of knowledge, we join a cosmic conversation that extends far beyond our planet and possibly beyond our universe. In this grand exploration of reality's structure, every discovery brings us closer to understanding our place in the vast, possibly infinite tapestry of existence.